Okay, sounds good. And will be the proctored practice exam. It shouldn't be counted for the grades, right? For
It
what
won't.
we have.
No, that was just
It's just
to see if you can figure out what you need to figure out to get online and that sort of thing.
okay. Thank you, brother.
Mm-hmm. Okay. Okay, so this one here, we have given some equations and we want to calculate the standard enthalpy of formation for copper oxide. This is not the whole name, copper oxide. Could somebody, Alyssa, could you tell me what the name of this compound is?
Copper, sorry, I'm trying to get a periodic table. Copper 2 sulfate?
Oxide,
Or,
right.
Okay, yeah.
Yeah, very good. Copper 2 oxide. And that's because the copper ions in this compound have to have a +2 charge, right? Oxygen has a -2, so if it's a 1-to-1 ratio, the copper must have a +2 charge. All right, very good. So we want the standard enthalpy of formation for copper 2 oxide. Anastasia, do you know what it means, the standard enthalpy of formation reaction? What's the enthalpy of formation reaction look like? Do you know, Anastasia? Do you guys have an option to record this class somehow? Anybody out there?
Not that I know of.
I don't think so, but I'm not very tech savvy.
Okay. All right. Okay. Yeah?
Well, what I'm seeing right now on the screen is the session is not being recorded. So,
No, I don't record it with their recorder because it only lasts for a couple weeks or whatever, 14 days. So I record it and put it on YouTube myself, but I am recording it. But I'm just wondering if some people come on and they don't participate because they're not recording, or I'm just wondering if, or so because they're recording and they're thinking they're going to watch it later, or what. So just trying to figure out. Make sure we can answer questions when necessary. So, Brielle, tell me what you think the standard enthalpy of formation reaction is. Or how do we, what's the standard enthalpy of formation reaction?
The change of heat for the formation of a mole.
That's right, very good. The change of heat, delta H, for the formation of a mole of my stuff, so copper 2 oxide, from its what, Camilla? From its what? What do we start with in a enthalpy of formation reaction? We're looking at the delta H for the formation of 1 mole of material from what? Camilla?
I don't know, I'm sorry.
Okay, from its elements, So from copper, and how do I draw elemental oxygen, Camille?
Is it like an O with the 2 dots?
It's like this. It's
okay.
O2, it's oxygen gas. So these are how we find these elements in nature, right? Copper is a metal, oxygen is a gas like that. And so the delta H associated with forming this compound from its elements. Now I have to make sure that this is a balanced reaction, knowing that I'm only going to form 1 mole here. So let's see, Daisy, Daisy, what do I have to do to make this reaction balanced?
You have to put a 2 in front of the copper.
Okay. It would look like I'd have to put a 2 here and then maybe a 2 there, right, Daisy?
Uh-huh.
But this is asking for a standard enthalpy of formation reaction, right? So in a standard enthalpy of formation reaction, we're only making 1 mole of this material. So if I only want to make 1 mole of this material, what I actually have to do is reduce the number of oxygen atoms represented here on the left side by putting a 1/2 in front. Does that make sense, Daisy?
Yeah, I didn't realize that. I always forget about the fractions, but to make it have 1, you just put the 1/2 in front. Okay.
Right, and we do that because, again, only in the special circumstances when we're talking about the enthalpy of formation reactions, right? Okay, so now I am aware of the chemical reaction that I'm trying to identify the delta H for, right? I need the delta H for this chemical reaction. Oh, why is it doing that? Can't see my writing? Or maybe I need to put it more towards the middle. There we go. Okay, so now can I combine these chemical reactions? I got 3 chemical reactions given to me. Can I combine them in a way that after I add them or subtract them, I will get this reaction? Any ideas, Ephraim? Which of these reactions should I use and how? Joey, are you there?
Yeah, sorry, my computer kind of glitched out for a second.
Okay. So Ephraim says, I get the first one. Yep, I'm going to need the first one. And the way we can tell is because we need copper all by itself. And the first one is the only one that offers copper by itself. Very good. So how are we going to use the first one? Ephraim, any ideas? I mean, can I use it just like it is? Joey, do you know? Can you tell?
Well, the first equation has 2 coppers, and so do we have to cut it in half?
Yeah, I'm going to have to use half of that first equation. So I'm going to use the 2 Cus. I'm just going to cut it in half right as I write it. 1/2 sulfur forming Cu. Let's see, what is this? Forming 1/2 Cu2S. Very good. And so now the delta H for this reaction is what, Rebecca?
Isn't it just negative 79.5 divided by 2?
That's right. Negative 39.75. Okay, excellent. The second reaction, Rebecca, how do you think I can use that second reaction?
To get the S by itself?
The sulfur, do I want sulfur in this bottom reaction anywhere? Or it's going to get rid of this S maybe? Is that what you're thinking?
Maybe, I don't know.
Okay.
I'm confused now.
Well, it's possible. So let's see. I don't know. Do you see a way that we can use the bottom reaction anyway?
The one that's Cu2S plus 2O2. That one?
Yeah, can we use that one anyway? Is that useful for anything?
To combine the sulfur with the oxygen. Maybe.
Okay. So remember, what we're doing here is we're trying to add up reactions to get this thing down on the bottom, right? So we chose this one because it had our reactant in it. As it was written, it was 2 Cus, but we cut it in half. And whoops.
Because it had copper by itself already?
Yeah. And because we only wanted 1 copper, we cut it in half, right?
Mm-hmm.
Okay, so it looks like we can use this last equation because it's the only place where we're given information about our product, which is copper 2 oxide, right?
Yeah.
But I don't want two of them, so it looks like I'm going to also have to cut this one in half, true? So I'll go 1/2 Cu2S plus an oxygen gas to yield a CuO and 1/2 SO2. What's the delta H for that reaction, Zaf? Okay, so the reaction without cutting in half up here, right, was a negative 527.5. So if we take the negative 527.5 and divide it by 2, divided by 2, because that's what we did for this reaction, negative 263.75. Okay, Alyssa, what's next? What does it look like I need to do next?
So, I think we'll have to do the use the sulfur oxide to help get rid of the sulfur on both sides of the equation.
Okay. Very good.
So
how are we going to do that? Can I write it down just like it's written here?
Yes. I think so, because then you have the sulfur oxide in the product, which you're gonna take out from the product side, and then the reactants are on the reactant side.
But don't I have the sulfur dioxide in the product side already as it's written now?
Oh yeah, so it needs to be flipped, sorry.
Okay. So I need to get that reaction, SO2 on the product side, S and O2. But I also need to do one more thing. What's that?
We'll have to divide it by 2 again.
That's right, divide by 2. We knew we had to... Yeah? What will it be?
It will be divided by 2, but it will also be positive since the reaction.
297 positive this time, divided by 2. Whoops. 148.5. So positive 148.5. Okay, so how did we know that? We knew that because we had sulfur oxide in the product. So we needed to get the sulfur dioxide in the reactant side. And it works out well because the sulfur needs to be gone. Our oxygens, are our oxygens doing what we would like them to do? Yeah, because we have 1 oxygen here and a 1/2 of oxygen here in our product side, and we only want to end up with a 1/2 of an oxygen. So it looks like things are going to work out nicely. The 1/2 copper sulfide, copper 1 sulfide disappears. This is copper oxide. It ends up being here, right? 1/2 sulfur dioxide disappears. The 1/2 sulfur product side, reactant side, and then this and this. This is 1 mole, 1/2 a mole, so 1/2 a mole makes this down to 1/2 a mole. I should really just leave it like that. Okay, so the delta H for this reaction should be just the combination of those 3, like that, right? So I got a negative 39.75. Plus a negative 263.75 plus a 148.5. Okay, so negative 155 should be my delta H for that reaction. Okay, and we should look it up to make sure. Yeah, go ahead.
Just from the original equation, like the Cu plus O2 is CuO, why don't we just use O instead of O2? Can it not be by itself?
So are you saying, are you saying why can't we just take this first equation and put an oxygen in there?
No, I was just wondering like why we use Cu plus O2. Why couldn't it just be Cu plus O?
Oh, I see. Okay. Yeah, the
'Cause-
definition of a formation reaction is combining the elements in their standard states. So, which is elements how you would find them in nature. And oxygen is found as O2 in nature. So.
Okay.
So this is 773, which is not in the back of the book. So I'm sure that's the answer though. Okay, very good. Did anybody get to find a different question that they want to go over?
I have a question from like the last review, like the quiz, the 9.6 to 9.1.
Yeah.
I'm just confused about what resonance structures are.
Okay. Resonance structures.
Yeah.
Okay, let me see if I can bring up that question. Is that all right? Yeah. Quizzes 9. It's the most recent homework, right?
It's the one with 10 questions on it.
Okay, so like this one here, question 3.
No, it's just it says like how many resonance structures does a molecule of carbonic acid have?
Okay, question 4 here then, right?
Yeah, 4.
All right, so we need to know what carbonic acid looks like. Do you have any idea what carbonic acid looks like, first of all?
COH?
What is it?
HCO?
Okay, what? So what's okay, so this is another small, probably least or less important, but there'll probably be a question about naming acids, right? Carbonic acid, what kind of acid? Binary or oxy?
Oxy?
Oxy. So we take the polyatomic ion. What polyatomic ion does carbonic acid have?
CO3.
CO3. What's the charge on it?
-2.
Right. All right. So once we know it's a CO3 2-, we know that its acid must have how many hydrogens?
2.
2. H2CO3. Very good. So that's the thing that we need to draw the resonance structure of, right?
Mm-hmm.
Carbon in the middle, 1, 2, 3. The hydrogens are coming off like this. We count up the electrons, we start drawing, and I think we probably end up with something that looks like this.
Uh-huh.
All right. And now resonance structures. What is a resonance structure? Resonance structure is where the double bonds ended up being on a different atom, right? So instead of having them drawn over on the left here, we could draw them at the top and have the hydrogen scoot over that way. Right? Those are resonance structures of each other. All that's happened is that this electron density here moved up onto this oxygen atom. This electron density moved down here. This electron density moved in there. And then this electron density here goes and grabs an H+. All right? So in the end, we have the hydrogen moving from the top down to the bottom left here, and we have a different resonance structure. Okay, is there another one we could draw? Was that you, Camilla?
Yeah.
And is there another one we could draw, another resonance structure, or is that the only one?
There was the carbon tetrafluoride.
Well, I mean, for this, are we done with this answer, this question?
Sorry.
So we know we got 1, 2 resonance structures. Is there another one? So essentially, what this question is or what resonance structures are, is recognizing, this time I'm just going to draw the carbonate ion itself, is that this structure here, or these three structures in this case, these three structures, negative sign here, negative sign here, negative sign here, negative sign there, right, are all occurring at the same, in the same molecule at the same time, essentially. It's bouncing back and forth so fast that when you measure the length of these bonds, it will be the average of a double and two singles. Or if you measure the energy that it requires to break one of those bonds, it'll be the average of how much energy it takes to break two of these carbon-oxygen bonds and one of the carbon-oxygen double bonds. So here we see that we have three possible resonance structures, three locations where those double bonds can move around. Does that make sense, Camilla?
Yeah. So the answer is 3?
Should be.
I put that and I got it wrong.
Oh, really?
Wait. Oh, just kidding. Sorry, I was looking at the carbon tetrafluoride.
Okay. Well,
Yeah,
was that one talking about, okay, carbon tetrachloride, was that one talking about resonance structures?
Yeah.
Oh, right. What did you decide for that one then? What do you think carbon tetrachloride can have?
I don't know.
Well, here's carbon, well, CCl4, true? Is that carbon tetrachloride?
Yeah.
So we draw the resonance structure, or the Lewis dot structure, and it looks like this, right?
So you'd have 4 different?
No, because there's no double bonds here, right?
Okay.
So there's just that one. Does that make sense?
Okay.
I can't draw this structure any other way. Resonance structures are only when electron density can move in a different way. I'm not going to be able to get electrons
only
when there's double bonds, right?
Okay. Okay. Thank you.
Yeah. Anybody else have a question about anything? Okay, how about number 17 here? Whoops. The sizes of metal atoms generally increases progressively from top to bottom, generally increases progressively from left to right, are smaller than those of the corresponding ions, do not change upon losing electrons. 17 there. What do you guys think?
Would they not change?
The size of metal ions would not change upon losing electrons?
That would be my guess, but I think I'm...
Okay. What do we know about the size of, what do we call an atom once it's lost an electron? Give me an example of an atom that loses an electron. Alyssa, what's an example of an atom that likes to lose an electron?
A metal atom or just an atom in general?
Well, do metal atoms like to lose electrons?
Some of them do.
Yeah.
Yes.
Which ones like to lose just one electron, for example? Give me an example.
Lithium.
All right, very good. So we got lithium atom. And if a lithium atom loses an electron, then it becomes...
An ion?
Yes, a lithium plus ion. What's larger, the lithium atom or the lithium ion?
Are you still asking me?
Yes.
Oh, okay. Well, wouldn't the original lithium ion be larger because it has a larger electron field?
Okay, So once this has lost an electron, all of the protons can give more attention to the remaining electrons, and so the resulting species is smaller. A cation is always smaller than an ion. So the answer, it does not change upon losing electrons, is not true. So D is not right. Anastasia, are you there?
Yes.
All right. Any ideas on this one? The size of a metal ion?
Increases.
Are smaller than those of the corresponding ions. Is that true? C?
I think so.
You think so? What do you think, Brielle? Does C sound okay?
I'm gonna say no because of the example we just talked about, how the ion is already smaller than the atom.
Okay, very good. So it's not going to be C. How about B, Camilla? The size increases from left to right along the periodic table.
Well, I know that like the negativity increases.
Okay.
When you go to the right. So that would just make it smaller, wouldn't it?
All right. Well, let me bring up a periodic table here. Let's think about the size of something like sodium and magnesium. Sodium and magnesium. Okay, I'm going to move the periodic table over here a little bit so we can think about or keep it in mind. Size of sodium compared to magnesium, right? And to do this, we kind of have to remember what our elements look like. This is, let's see, what's the noble gas? Neon. This is the electron configuration for sodium is neon with a 2 or 3s 1, whereas the noble gas electron configuration for magnesium is neon, neon with a 3. How does it differ, Camilla?
3s2.
3s2. Very good. So which one of these is going to be larger, sodium or magnesium?
Magnesium?
We might say, well, magnesium's larger because it has another electron. However, remember, 3s1 and 3s2, the space where that electron is going to go in is in the same location, right? It's not in a larger location. It's actually just filling in that second electron in that orbital, right?
Okay.
So the electron's not making it larger. Is there anything else that's influencing the size, Camille?
The answer is yes, but I don't know what.
Yeah, we've increased the number of what when we went from sodium to magnesium? We increased the number of electrons, but we also increased the number of what, Camille?
Protons?
Protons, that's right. So if the electrons aren't going in an outer shell that's larger than the previous one, then the magnesium with its extra proton is actually going to pull everybody a little bit closer. And remember, my analogy was if you're walking in the mall with a bunch of kids and you have a certain number of parents, the kids will kind of roam and the parents will kind of tell them to come closer, and so they'll be in a region. If you have more parents and the kids are kind of in the same hallway size, you could say, same orbital, then the parent or the kids are going to come closer together. Okay? So it generally increases progressively from left to right in a period. That's not true. As you go from left to right in a period, now let's look at these periods, right? Anywhere along here, as you go left to right, all of these electrons are filling in the same subshell, so the orbitals aren't getting larger. All that's changing is the electrons are getting more electrons in the same orbitals, in the same subshell, but the number of protons is increasing. So your size of your atom decreases as you move left to right. So that one is not true. The size of atoms as you go left to right on the periodic table generally will decrease. So all we're left is A. generally increases progressively, so the size of the metal atom increases progressively from top to bottom in the periodic table. Now we know it's true, but why is that true, Daisy? Why is it true that the size of metal atoms generally increases from top to bottom?
Is it because they, like you said, they're just gaining more subshells?
They're in a higher subshell, right? So magnesium to calcium, for example, neon, 3s2 for magnesium, but calcium, argon, 4s2. So those electrons are in a larger s shell, and so that's why you get an increase as you go top to bottom. Okay? Any questions about that one? Anybody have one that you want to go over?
So the answer to that one is B, correct?
It was A.
Oh.
The size of metals generally increases from top to bottom. It doesn't increase as you go left to right. It actually decreases when you go left to right. Let me see if I can find another one here. All right, looking at number 22 here. Ephraim, any ideas for this one, number 22? Which of these ions is the smallest? Now, isoelectronic, we can look at, we might not know what that means, isoelectronic. Iso means same, electronic sounds like something to do with electrons, but maybe that's not enough to know what's going on. But we can look at the elements or the species that they're kind of showing us here. D, he says, which one is the smallest? D, let's see, we have aluminum, sodium, fluoride ion, and the oxygen ion. So sodium ion here has lost an electron, and oxygen has gained 2 electrons. Fluoride ion has gained an electron, and aluminum ion has lost 3 electrons. So what, you want to give us some reason why you decided to choose D, Ephraim, or what you were thinking? Because of the charge, all right, the -2 charge. What do you think would be larger, Ephraim? An oxygen atom or an oxygen ion, 2- ion? Which is larger? Any idea, Joey? What do you think? Which one of these would be larger?
Isn't the original element usually larger?
Okay. The element here has 2 fewer electrons. In this case here, where we've given it 2 more electrons, those electrons are going to make the species larger. Now you could say, well, and we can use the electron configuration here as well. Electron configuration for oxygen is neon. Two s2, 2p4, all right? And then the electron configuration for oxygen with the -2 charge is the same thing, 2s2, but now we have 2p6. Now those electrons went into the same shell, same subshell, so you could say, oh, those electrons are not going into a larger subshell. But there's something else that's happening here as well. The number of protons is not increasing. We added 2 extra electrons and we haven't increased our number of protons. And so those 2 extra kids will make a larger species. So anionic species, if all you do is increase the number of electrons and you don't change the number of protons, then oxygen, or the ion, will always be larger. Okay? So that being said, we should probably not think about F- and O2- being larger because they're actually gaining more electron density. Okay? And isoelectronic, if isoelectronic means that all of these have the same number of electrons. So if we look at oxygen with a 2-, we see that it has 8 as an atom, and so it has 10 electrons here. Fluoride ion, 9 as an atom, 10 electrons. Sodium ion, 11 as an atom, with a plus charge, 10 electrons. Aluminum atom, 13 electrons, plus 3 charge, 10 electrons. So all of these have 10 electrons. So if they all have the same number of electrons, what's going to determine their size? Aisha, you want to write down there? What do you think is going to determine their size if they all have the same number of electrons? The number of protons. That's right, the number of protons. So because the number of protons is going to determine their size, what do you think, Ephraim? Which one is going to have be a larger species then? Or sorry, we're looking for the smallest. Which one's going to be the smallest species? Ephraim, are you there? Which one, Aisha? Which one do you think is going to be the smallest species? That's right. Very good. Aluminum is going to be the smaller species because it has the most number of protons and the same number of electrons as all the other species there. Okay. Very good. Does anybody else have another question that they would like to go over specifically from the book or a quiz or anything?
I had a question.
Great.
It's from the last quiz again. When it's talking about lone pairs of electrons, is it like when you count the lone pairs, are you counting the individual electrons or are you counting the pairs?
It depends on the question. If it says how many lone pair electrons, then it's just asking for the electrons. But if it just says how many lone pairs, all right, then it would be talking about the pairs, the lone pairs. So this one here is asking for lone pair electrons. So that's the individual electrons. Did you want to go any further into that one, or do you think you understand that one?
And then what's the difference between lone pair and non-bonding?
Not really anything. Lone pair electrons are going to be non-bonding electrons.
Okay.
Did you want to finish that one up, or do you think you got it?
I think I got it.
Okay. Does anybody else have a question that they want to go over? Okay. Let me see if I can find another question here. Here's a question. Oops. Number 6 here. What is going on? Oh, there we go. Number 6, which change requires an oxidizing agent to produce the indicated product? Which change requires an oxidizing agent to produce the indicated product? All right. Alyssa, should we work through this one? Everybody should kind of be looking at it and trying to do it. What do you think, Alyssa? How would we approach this one? What would we want to know?
Well, you'd want to look at the different like changes in electrons if they're giving up electrons or taking electrons.
All right.
And like where they're going in each reaction.
Very good. Very good. So, can you see any that stand out really quickly in terms of, are we looking for an oxidation reaction or are we looking for a reduction reaction?
We're looking for a reduction reaction that requires an oxidizing agent.
Okay, because oxidizing agents reduce?
Yes.
Are you sure?
I thought I was sure, but now I'm not so sure.
Well, I mean, so I'm an oxidizing agent. I have my gun, and what do? I go around and do what to people?
You give them electrons.
Do I oxidize them or reduce them? If I'm an oxidizing agent, do I go around oxidizing people? Is that my job, or do I go around reducing people?
You oxidize people, which causes a reduction reaction.
Well, if I oxidize people, then they are being oxidized.
Oh, okay. I'm confused now. I thought I got it, but now I'm confused.
So, if you're the oxidizing agent, you go oxidize somebody, right?
Yes.
So these are all half reactions. They're not full reactions. We're not seeing whatever the other step is, because you can't just have one thing oxidized by itself without something else doing it. But apparently they want to know which one of these would require an oxidizing agent. So we need to look for a process that is an oxidation. So, any of them stick out, Alyssa, as an oxidation?
To me, the zinc sticks out because there's not like another element that could supply the other electrons.
Okay, so that's easy to look at then. Let's look at zinc plus 2 going to zinc metal. Is this process gained or lost electrons?
It's being reduced.
It's being reduced.
It's losing electrons.
So what does that tell us? It's not going to be B. True?
Yeah, yes.
All right, very good. So we got one out of the way. How about D? SO3 going to SO4 2 minus. Is this an oxidation reaction?
No, it's a reduction reaction.
Okay, how can we tell?
Because electrons are being lost in the reaction.
Well, because of this thing here?
Yes.
Let's identify the oxidation number for all of these elements in the reaction, right? So what's the oxidation number for the sulfur here?
7.
All right. Oxygen here is a -2, right? Each oxygen is a
yes,
-2.
sorry, I was looking at electron number.
All right. So total is -6. So sulfur must have been a what? Whoops. Whatever the sulfur is plus whatever the oxygens get are supposed to give us a 0, true? Because there's no charge here. So that means sulfur must have been a +6. Can you see that?
Yes.
All right, so if sulfur
Yes.
was a +6 on this side, let's see what it is over here. Oxygens are -2. There's 4 of them, a total of -8. Something plus the -8 is supposed to equal what on the right here, Alyssa?
-2.
-2. Very good. So that means it looks like a +6. Is that true?
Yes.
All right. So the sulfur didn't change oxidations here. So that was not an oxidation. All right. Let's look at ClO minus going to Cl minus. What's the oxidation number for the chlorine here?
7.
7?
Mm-hmm.
Well, let's remember how we do oxidation numbers, right? Oxygen is a -2. True? And then whatever
Yes.
chlorine
so
plus the -2 has to be what?
-1.
-1. Very good. So what's the chlorine's oxidation number?
1.
+1. All right, so it went from +1. What's the chlorine's oxidation number on the right?
-1.
-1. So is that an oxidation or a reduction?
A reduction.
Okay, so now we saw that B was a reduction and C was a reduction. So if we thought we were looking for a reduction, our question would be really confusing because we want to know which one is the answer, right? So let's look at A, and D is not an oxidation or a reduction. Let's look at A and see if we can see if this is an oxidation, okay? What's the oxidation number on the sulfur on the left? S2O3 2-. What's the oxidation number for the sulfur there?
Is it +2?
+2, let's see. There's 3 oxygens, so that's a -6. Whatever the sulfurs are plus the -6 has to equal -2. So you said a +4, and that would make each sulfur a +2. Good, good. How about on this side over here?
Um, 5. Oh wait, there's 4 of them. Just a second. It would be 10 divided by 4. Can they have partial charges?
They can. They can. Partial oxidation numbers. Let's see. Did we do that right? So this needs to be 10. So 10 divided by 4. What is that? 2.
2.5.
2.5. So a positive charge of 2.5. Is that an oxidation or a reduction? Going from +2 to +2.5.
An oxidation.
That is an oxidation. All right, so that one is going to be the situation where an oxidation reaction, oxidizing agent is required because this is an oxidation.
I have a question. I think I'm just a little confused. Like when it says oxidizing agent, is that gaining electrons?
Well, I mean, if somebody says oxidizing agent, your oxidizing agent will be the one that's gaining electrons, because if you're oxidizing somebody, you're taking away electrons from them. Is that what your question was? Will the oxidizing agent be gaining electrons?
Yeah.
Yeah, that's right. Oxidizing agent will be gaining the electrons.
So I don't see like how on A that's gaining electrons.
Well, they're not asking which one of these is the oxidizing agent. They're saying which one of these processes will require an oxidizing agent. So what we saw was that C is gaining an electron, and so it would require another species to be losing an electron, which would be a reducing agent. If a reducing agent is around, it will be reducing somebody. B, this species was gaining 2 electrons, again, would require a reducing agent. D, this species is not changing oxidation numbers, so it wouldn't require either. This one is becoming oxidized. Therefore, if this is going to occur, it's going to need an oxidizing agent. So which change requires an oxidizing agent? It would be this one here.
Okay.
So Aisha wanted to go over this question here. In a phosphorus-oxygen bond, has that energy. Let me get this here. Okay. How do we answer this question? Energy is given for a phosphorus-oxygen bond and the energy for a phosphorus-oxygen double bond. And then we're asking, what is the average energy, bond energy, of the phosphorus-oxygen bonds in phosphoric acid? So initially, this requires us to know what phosphoric acid looks like. Anastasia, do you know what the chemical formula for phosphoric acid is? Camilla, do you know the chemical formula for phosphoric acid? Are you watching, Aisha? Are you ready for this problem? Okay, she's there. How about you, Aisha? Do you know the chemical formula for phosphoric acid?
I think I know it.
Oh, go for it. What is it?
Is it H3PO4?
Very good. H3PO4. So we got H3PO4, phosphoric acid, and we're going to draw the Lewis dot structure because we need to know how many single bonds are in a how many phosphorus oxygen single bonds and how many phosphorus oxygen double bonds there are, right? So the Lewis dot structure. Why don't you guys see if you go to your, I'm going to bring this over so we can look at this. If you go to your little thing right here, see how I can go here and I can click right there and I can set my status. I can give a thumbs up, right? See now I'm a thumbs up instead of whatever I was before. If you could give me a thumbs up if you want to be asked questions, because we need to see who's interested in this and we need to move along as fast as we can so that we can get to other questions. Otherwise, we're going to be here till midnight. So give me a thumbs up if you're listening and would like to answer questions. 5 seconds. If you're not listening or you just don't want to answer this one, then give me a thumbs down. Yeah, give me a thumbs down. And also, we'll do that for every question. So if you're listening and you want to answer, give it a thumbs up. If you're not able to answer for whatever reason, give me a thumbs down. And so when I go through that list, I won't be asking anybody questions. Or if you can just leave it how it is, if you don't want to answer, you don't have to give a thumbs down, I guess. Okay, so H3PO, yeah, go ahead.
How do you get to the thumbs up thing again?
Okay, so do you see this on your screen, hopefully? A little list of everybody's names. If you just click on your name, left click, and then you set status, and then you can choose what you want to do. And this is going to tell me if you want to be interacted with, thumbs up, thumbs down. I don't want to be interacted with for this question or at all. I got somebody in the room, I'm busy, blah, 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 whatever. Okay? So
thank you. That's
the way that I'll know who I can communicate with. All right, so let's see. So Camille, we're going to draw the Lewis dot structure. Central atom, what's the central atom, Camille?
Is it the PO4?
The central atom is the phosphorus and then the oxygens around it. That's right. Very good. Where do the hydrogens go, Camilla?
They go on the oxygen.
Yeah, coming off of the oxygens. Very good. Daisy, how many electrons in this, how many electrons in this whole thing? Do you know, Daisy? Can we add that up?
Yes. Give me a second. Is it 26?
26. Phosphorus brought 5. 4 oxygens. That's 24.
Oh, I didn't see it. I just counted 3 for some reason.
And then 3 hydrogens. That's 3.
So it's 32.
32. Okay. So we got 32 valence electrons. Very good. So how many do we got all on there already, Ephraim? How many electrons do we have on already? How many electrons do I have written already, Ephraim? So each bond represents 2 electrons. Go ahead, Camilla.
14.
14. 14 electrons. That's right. So I have, how many left? 8, is that right? No.
18.
18. 18 valence electrons left. All right. So, Alyssa, where am I going to put my electron density?
On the rest of the oxygen.
Okay. So, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Did I do that right?
Yeah, I think so.
Okay. So is my structure done, Joseph?
Well, phosphorus only has 4 right around it, and it should have brought 5 to the party. So that one isn't satisfied yet.
Okay, it has a, what's its formal charge?
That would be +1.
+1. Very good. +1 formal charge. So how am I going to, is there any, other atom that has a problem?
The oxygen on the far left.
Okay. So we have
7, right?
a formal charge distribution that doesn't look very happy, especially when those 2 atoms that have those formal charges are right across from each other. That's an indication that there's generally not something happy going on. So how are we going to fix that, Joey?
You can make a double bond.
By bringing in that electron density, right?
Yeah.
Okay. So now that we've finished our Lewis dot structure, right, we can answer the question about this. Are you ready for the answer, Aisha? Are you there? Great. Okay. So what we want to have is the average bond energy of the phosphorus-oxygen bonds in phosphoric acid. So the average energy is going to be a single, a single, a single, 3 singles, and 1 double. Because, like we mentioned before, this exists in multiple, what we call, I'm blanking on the word, resonance structures, multiple resonance structures. This could also have been drawn with the oxygen on top having the double bond and this oxygen having the hydrogen, right? In fact, how many different resonance structures could we have drawn? So the question wasn't how many resonance structures does phosphoric acid have, but it could have asked that. How many resonance structures would phosphoric acid have had, Anastasia?
What's the question again? Sorry.
How many resonance structures does phosphoric acid have? I've drawn 2 for us so far, 1 here and 1 here, right? Are there any others that could exist?
Wait.
One, 2, right? I can also have the oxygen double bound there.
Right.
Any more?
On the
right, like that?
yes.
Okay, very good. So there's 4 different resonance structures. And, you don't have to draw them all out to know. You can just recognize that oxygen is going to be able to be double bound either 1, 2, 3, 4 different spots, right? 4 different spots. And all of these would have negative charges on the phosphate ion, right?
Right.
Okay, very good. So the average energy, bond energy, is going to be three of the singles, which is 225, plus 1 of the doubles, and then that value divided by what? Divided by what? Camille?
Me?
Say that again?
Me?
3?
No, me or Camilla?
Oh, Camille. Isn't Camille? Oh, yeah, Camille's turn.
Me.
Camille. 225 times 3 plus the 580. That value, 1255, divided by what?
4.
4, that's right, because there's 1, 2, 3 different 4 bonds, phosphorus oxygen bonds in these resonance structures, right? So that value divided by 4, hopefully the answer is up there somewhere, 313.75 or 314. Did that make sense, Aisha? Okay, great. Are there any other questions that anybody have specifically that they want to go over?
I'm not sure if you already explained it, but where did the 3 come from where we multiplied with the 225?
If we look at any one of these resonance structures, all of them are going to have 3 phosphorus oxygen single bonds, right?
Oh, right.
That's our 3, 225, and each one's going to have 1 phosphorus oxygen double bond, and that's where we got our 580, right?
Thank you.
And then why did you add them? Sorry, like why did you choose to add the 3 times 225 and then with the 580?
Well, I'm just taking the average, right? So I want to know the average bond energy, the average bond energy. The bond energy of 1 is 580. That's the bond energy of this one. The bond energy of this one is 225. The bond energy of this one is 225. And the bond energy of this one is 225. So to find the average, I add them all up, divided by 4, because there's a 4 total, right? Good. Anybody else have a specific?
I have a question.
Yeah.
About this question here. So on the test, it's just going to look like that. But how? Like, I didn't know that there was 4 oxygens for 1 phosphorus. So are we just supposed to memorize the structures, or like? Because I wouldn't have known. Oh, there's 4 oxygens.
Oh, for phosphoric acid, you mean, or what?
Yeah, for this question.
Well, so yeah, initially we said we need to know what phosphoric acid is. All right. So after we know what the chemical formula for phosphoric acid is, H3PO4, then we need to be able to draw the Lewis dot structure for that, right? And so once we started to draw the Lewis dot structure, we know it's an oxyacid. We know the hydrogens are going to come off there. So that gave us our skeleton structure. Once we had our skeleton structure, we added up number of valence electrons, started working everything through. Whoops, this is 1 more hydrogen there. Started working everything through, and then realized that we needed to have a double bond here to reduce formal charges the best, right? And so that's how
sorry, I joined late. If you already described this, sorry about that. I joined a little bit late.
That's fine.
Okay, that makes sense. Thanks.
Okay. Any other questions about this or any other question? About let's see, about anything.
Sorry, another question about this question.
Yeah.
Dividing by 4, is that because there's 4 bonds in the skeleton structure, or is it because there's 4 resonance structures?
It's because of the number of bonds, right? The number of bonds. Yeah, we only answered the resonance structure question because we had a question like that earlier where we were asked how many resonance structures the carbonate ion had. And so we had answered that one. And see, when the question is asked, what is the average bond energy of the phosphorus-oxygen bonds in phosphoric acid? They don't need to say, what's the average bond energy? They can just say, what's the bond energy of a single phosphorus-oxygen bond? All right. If they said, what's the bond energy of a single phosphorus-oxygen bond in phosphoric acid, they don't mean a single bond. They just mean an individual one, right? And if I asked you right now, Joey, could you answer this question? What's the bond energy for that bond? It would be kind of a trick question, right? You'd want to say 225. However, what you need to take into account is that this type of molecule exists in these 4 different resonance structures simultaneously. And so the actual energy that it would require to break that bond wouldn't be 225. It would be, what do we decide here, 314, because in reality, it's 75% of the time it's 225, but then 25% of the time it's 580. And so the actual energy to break that bond here would be the 314. So in a way, we have to recognize that there are multiple resonance structures that are possible.
Okay.
If you wanted to think of it in terms of resonance structures, you'd have the same ratio, right? Because 3 out of the 4 here are single bonds, and then 1 is a double bond as well. So you'd get the same ratio up here. Okay. Anybody have another question specifically that they want to go over, or should I choose one from our review manual?
I have one question about what is the predominantly covalent mean?
Okay, predominantly covalent. So if I get some, make some elements up here. So we got FeCl3, FeCl2, ZnNO3, HNO3. I'm going to add one more, PCl3. There we go. Okay, so which one of these is predominantly covalent? And now the answer is often in the names of the compound. If we can know the names of the compound, we kind of know which ones are predominantly covalent. Let's see, was this Camilla that was asking this?
Yeah.
You want to give me the names for these compounds?
Okay. So that'd just be I'm sorry. Sorry, I don't really know.
All right. This is iron 3
Just iron
chloride. Right, iron 3 chloride. Because,
so then iron chloride.
Go ahead. It's what?
So then the next one would be iron 2 chloride.
Uh-huh. Now, why did we name them those? Why did we name this iron 3 chloride and that one iron 2 chloride?
3+ charge in the first one.
Yeah, iron. This one has a +3 charge. This one has a +2 charge. How about this one here? The next compound.
Is that zinc? Zinc.
Yep.
Nitrite.
Nitrate. NO3. Very good. Zinc nitrate. All right. And then HNO3.
Is that hydrogen nitrate? Hydrogen 3 nitrate.
Okay, close. It's specifically a kind of compound that begins with hydrogens. What do we call those?
Oh, acid.
Yeah. So what's the name of that acid?
Nitrate acid?
No. The 8 ion goes to nitric acid. Nitric acid. Very good. How about this last one here? What's his name?
Oh, is that like triphosphorus chloride?
Okay, it's phosphorus.
Trichloride.
Trichloride. Very good. Now, why did we have to name that differently?
Because they're nonmetals.
They're nonmetals. That makes it a molecular compound. And molecular compounds, we can bring this over here again.
Covalent.
Covalent, right. So which one is predominantly covalent? It's going to be this one here.
Okay. Thank you.
Yep. Good question. Okay.
Question. I have to go, but is there going to be lab tomorrow?
I'll be there, I guess, if anybody wants to talk about anything, but that's the way it is for everything. So, I mean, if you want to email me and tell me, hey, I have a question about this, we can set up a time that's other than our lab time, but I'll check in and see if anybody has any specific questions at lab time.
Thank you.
Yep. All right. Anybody else? I mean, I don't want to keep you guys. If you have stuff to do, you should leave. But if you want to keep working, I don't mind staying here and keeping working. So if you want to give me a problem that we should go over, we can do that. Otherwise, I'll keep choosing from here and we'll get problems to go over. Here's one. Number 18 here. What volume of 12 molar HCl is required to prepare exactly 500 milliliters of 6 molar HCl, or 0.6 molar HCl? Okay, who wants to help me with this one? Ephraim, Anastasia, and Camilla are willing to help. Chance, I think you came in late, but we've decided that if you're willing to help, then you can change the thumbs up sign on your little notification here by clicking on your thing. Clicking on your thing, saying set your status, and then you give yourself a thumbs up if you're wanting to help. Does that make sense, Chance?
Yeah, that makes sense.
All right. So, Ephraim, how would I approach this problem? What would I do? conversion. Well, does this look like a dilution problem, Ephraim? How would I do a dilution problem? Okay. Anastasia, do you remember the dilution equation?
I'm not sure.
Okay. So then let's have a little conversation about how we can remember what the dilution equation is. Do you remember the story I told you? So how we can remember the dilution equation? You remember, Anastasia, how the story to remember the dilution equation?
I don't think so.
Okay.
I remember.
All right. The story is about going to a party, and when we get to the party, we're all upset because we realize there's something wrong at the party. Do you remember what's wrong at the party, Anastasia?
Is it? I'm guessing. Is it the one that where some of those people that don't bring anything to the party?
It's not that one. It's the story about the punch being too sweet. Remember that? So if you go to a party and the punch is too sweet, let me get a orange pen here. If you go to a party and the punch is too sweet, right? And we knew this was a dilution problem because it tells us we're starting with 12 molar HCl and we want to go down to 0.6 molar HCl, right? Can you guys see that? So that's how we knew it was a dilution problem. So if I'm at a party and the punch I have in my cup is too sweet, and let's say I've got 400 milliliters of this punch that's too sweet, and let's say its concentration is, I'll just say, give some number, 10 molar, and I want this solution to be half as sweet, Anastasia. I want the solution's new concentration to be half as much. How would I make 400 milliliters of 10 molar half as concentrated? Any idea, Anastasia?
You add water?
That's right. I would add water. And if I want to add enough water so that it's exactly half as concentrated, how much water would I have to add to this punch here? So if you were at a party and you got sweet punch and you wanted it half as sweet, would you add the same amount of water as you had punch? Or would you add twice as much water as you had punch? Or half as much water as you had punch?
I think half.
Okay. Actually, you have to add the same amount of water if you want your new punch to be half as concentrated. The same amount of water. So your resulting volume here would have to be 800 milliliters, 400 milliliters of your original punch, 400 milliliters of water, so you need a slightly bigger cup, right? But now the concentration of this punch is only half as concentrated. So what's the new concentration, Anastasia?
20?
No, it's half as concentrated now.
Oh, sorry, 5?
So it's 5 molar. That's right. Twice the volume, but half the concentration. Okay? So we have to remember that story, because what that story is going to do for us is it's going to help our minds recalculate or identify the dilution equation. The dilution equation. And the way we do that now is we call this our initial volume. And this is our initial concentration. This here is our final volume, and this here is our final concentration. And now we need to find some relationship where we say, for example, C1 over V1. What is that equal to? C1 over V1, is that equal to CF over VF? Is that a true statement there? 400 divided by 10. So that's 40 over here. $800 divided by 5. That's 160 over here, huh?
Yeah.
So those are not correct relationships. Can you see that? So maybe C1 over V1 equals VF over CF. This is still 40. What is this now? That's 5 divided by 800. That's not going to be right.
5 divided by 800.
So that's not the right relationship. Can you see the right relationship, Ephraim? What do we have to do there? Can you see it, Anastasia? What's the right relationship? What is our dilution equation?
Sorry, I can.
What if we took this one, 800, divided by 400? That's 2, right? And then 10 divided by 5, is that 2?
It's 2, yeah.
So VF divided by VI equals
CI divided by CF.
CF. Okay, very good. That's it. That's our ratio. Now, generally, this is given as CIVI equals CFVF. It's the same statement, right? I've just kind of moved these up to there, right? So that's what usually people think of. But all you need to do is write down a problem like this, where you take an initial volume of some concentration, dilute it to half its volume, or twice the volume, dilute it down up to twice the volume, and get half the concentration, and then find that ratio. So then we can find the final volume, and that's what they're asking. What volume of 12 molar HCl, oh no, sorry, that's not the final, they're asking 12 molar is our initial concentration, and they want to know what volume of that 12 molar will be required to prepare 500 mils of 0.6. 0.6 is our final concentration, and 500 milliliters. These are molarity.
So is it 25?
Is it? Let's see. 500 times 0.6 divided by 12. Yep, 25. So C is the answer, 25 milliliters. Very good. Does that make sense, Ephraim? Okay, anybody else have another question they want to go over? How about number 6 here? Is this one we think we can do? What do you think, Aisha? How many electrons does the F minus ion have? Let me bring in a periodic table here.
10.
Yeah, 10 electrons. Very good. The magnesium 2 plus ion?
It would also be 10.
Oh, is that the answer?
Yeah, I think so.
What about bromine and selenium? Are they not the same?
Selenium would be 34, but then bromine would gain 1 and it would be 36.
Okay, very good. Aluminum here has 10, phosphorus has 18, neon 10, argon 18. Excellent. Maybe that one was too easy. Okay, Chance, do you have any questions you want to go over? Did everybody get to look at these problems over here from the quiz 960 to 9110 2? Yeah. Did you have a question, Aisha?
It's about the L value when there was this one question where it says that if an orbital can hold 10 electrons, which would mean it's the d orbital because the orbital holds 10 electrons.
Yeah.
And d corresponds to an L value of 2, so that would be the answer, right?
I think so. Was that not an available answer?
No, I think I got it correct. But my question is, would there be a situation where electrons be like 11 would be asked because none of the orbitals can hold 11 at that time?
Well, an F orbital subshell. How many electrons can be in an F subshell?
14.
14? Is that your answer or no? So if there is, so let's think of a question here. If there is a, subshell that has 11 electrons in it, what is its L value? Well, it can't have 11 electrons in an S or a P or a D subshell, so it would have to be an F. Is that what you're thinking, Aisha? And if it has to be an F, then what is the L value?
Yes.
0, 1, 2, or 3. Is that true?
Yeah.
Okay.
So would it be just 3?
Yeah.
So if the number of electrons falls into that orbital, then that would be the orbital. Then the L value corresponding to that orbital would be the answer.
Yeah, for that last electron, for that 11th electron, right? Because yes, there are electrons underneath that could be in P, D, or S subshells and orbitals. But if it's the 11th electron, then it can't be in S, P, or D, right? Because those S, P, and D can only hold 2, 6, and 10, right?
Mm-hmm.
Okay, good question. Let's see here if I can find another question that's good for us. Okay, here's one. Which of these are polar compounds? CO2 and SO2, CO2 and PCl5, SO2 and PFCl4, CO2 and PH3F. So let me rewrite that one. PH3F. Okay, so our answers are A, B, C, or D. What are we looking for? How do we know whether or not these are polar or non-polar compounds?
Isn't it that non-polar compounds share electrons equally, so there are no slight charges, like slightly negative or slightly positive charges, so the opposite would be polar compounds?
Okay, and then there's one other component as well. Remember the other thing? We want to find a bond that has some polarity, but then we also need to find something else. Do you remember? And it has to do with the structure of the compound.
I don't think I remember, sorry.
Okay, it's that the Lewis dot structure should be asymmetrical. Asymmetrical, right?
Oh, yeah.
So really, to answer this question, we need to be able to know what the Lewis dot structures look like. So carbon dioxide is one that we've dealt with a lot, so I'll just draw it up here. Is carbon dioxide a polar compound? Do we know? Anastasia, what do you think? Is carbon dioxide a polar compound?
I think yes.
Okay, so what are we looking for again? We're looking for polar bonds. And then what was the other thing, Aisha?
If it's symmetrical or asymmetrical.
Okay, if it's asymmetrical, what does that mean? Asymmetrical, does that mean it's polar or non-polar?
Polar compound.
No. I can't remember what I asked now.
You asked for asymmetrical,
Okay.
wouldn't
That's
that
right.
be polar compound?
That's right. Asymmetrical would be polar compound. Now, what about this carbon dioxide? Is it symmetrical or asymmetrical? It's symmetrical, right? Because there's a carbon in the middle. There's kind of looks like this, right? One thing in the middle, two things bound on the outside, right? It's a linear compound, and these things on the outside are exactly the same as each other. Carbon-oxygen is a polar bond, right? We can look at our periodic table and look at the location of these atoms. We can remember that nitrogen, oxygen, and fluorine are very electronegative. So the carbon-oxygen is a polar bond. However, the molecule is symmetrical. So just the presence of the polar bond isn't enough to make the molecule polar. And so these ones are not going to be polar. Does that make sense?
Yeah, it does.
Now SO2. Have we drawn SO2 before? Do you remember drawing it?
Yeah, I think so.
Think so? Anastasia, do you remember how to draw it?
I think so, yes.
Why don't you try to draw the Lewis dot structure for us here?
Okay, so. Oh, sorry. That's too big.
That's fine.
Oh. Oh. So O prime 6. O is 6. And also S.
Uh-huh.
So that is 12, 18 altogether.
Okay. 18 electrons?
Yes. So right now it already have 4. 3, and then so 1, 2, 3, 4. So that's 2, 4, 6, 8. And then I have 10 left. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
Okay, very good.
Okay, so I have to 3, 4, 5, 6. That's 6. Do you know how I can erase? Sorry.
Yeah, what you do is you just go to the pen color and you just choose blank. You want to erase these two right here?
Yes.
There we go. Okay.
Okay. And then sorry.
That's fine. Good.
And this one.
I'll erase those.
Yes, please. So like that.
Okay, very good. So, Anastasia, what is the bond angle between these sulfur-oxygen bonds?
That is it
It's a little less than 120, right? Because
yeah, is it 109.5?
No, it's basically 120, maybe 119, but it's just a little less than 120.
Mm-hmm.
And the way we knew that is because we have one region of electron density, two regions of electron density, and then a third region of electron density, right? So these try to spread out as far as they can, and 3 regions will be in the same plane. So the circle all the way around is 360. So divide that by 3. That's 120 each. Does that make sense?
Mm-hmm.
Is the molecule symmetrical or asymmetrical?
Asymmetrical.
Yeah, it's asymmetrical. You have symmetry down this way, right? From right to left, you have symmetry. But if you go this way, it's not symmetrical. The top has more electron density than the bottom, with the oxygens pulling the electron density away from the sulfurs because that oxygen-sulfur bond is a polar bond. So that molecule ends up being a polar compound. Does that make sense?
Yeah.
Did you follow that, Aisha?
Yes, I did.
Excellent. Now let's look at these ones here. Let's compare PCl5 to PFCl4. All right. Let me write that here. PCl5 compared to PFCl4. What do you think, Aisha? Are they both polar, both non-polar?
I think that PCl5 would be non-polar.
That's right. It would be very symmetrical, wouldn't it?
Mm-hmm.
But yeah, go ahead.
The other one wouldn't be because of fluorine.
That's right. It would not be polar because, I mean, it would not be non-polar. It would be polar. Whoops, that's too big. Right, because we would have P, and there would be an F here. 1, 2, 3, 4 chlorines. But the resulting electron density would be sucked up this direction. So if I was going to draw the electron density, these would be poorer in electron density, and the fluorine would have a lot of electron density because of the electronegativity of fluorine. Whereas PCl5 would be perfectly symmetric. Okay, let's ask this question. Do we know what is the let's see. What is the shape of PCl5? What's the shape of PCl5? Do you guys know?
Oh my goodness. I memorized this last semester.
So I think it just helps to draw it for ourselves, right? If we have a central atom, and then we have 5 regions of electron density, right?
Mm-hmm.
And if there's 5 regions, that means 1 is going up, 1 is going down. Whoops, that was bad. And then the other 3 are going where, Aisha? In equatorial positions like that, right?
Mm-hmm.
So, does that help at all? What is the resulting shape that this compound forms?
Trigonal pyramid?
Very good, but there's 2 pyramids, so it's trigonal what?
Bipyramid.
Very good. Trigonal bipyramidal. Excellent. Okay, are there any other questions? I have another class starting at 1. Do you guys want to go to that class and listen or not really?
It's Chem 106 also?
It's Chem 105, yeah.
Oh. Yeah, sure. It's good review.
Okay, let me make sure I can invite you to it. I'm not sure that it will let me do that, but let me try. Are you interested, Anastasia?
Yeah, sure.
Okay, let me try to.
Ê, tao còn cái là phải bịa không?
Yo.
Aisha, do you use your BYU email address?
What?
Oh, here it is. Your BYUH email address, right?
Mm-hmm.
You check it. Is that true?
Yeah.
Okay. Wait. It's live at BYUH on Microsoft.com. Is that what you do? Is that your email address?
Yeah,
okay.
I think so.
Okay. So check and see if, no, it doesn't recognize that one.
Maybe without the live. It's just at byuh.edu. Not, wait a second.
So what is your email address? LIONGI 1111
At byuh.
.go.edu or no?
Yeah, .edu.
It's not finding it.
Oh, it is at live byuh. Sorry.
At live.byuh?
Yeah. At live byuh.onmicrosoft.com.
L-I-O.
Oh, no. Dr. Scott, it's actually at go.byuh.edu.
And what is your beginning? Liongi Liongi 1111? Oh.
At
okay.
go.
Okay. Okay, so that worked. So you should be able to see an email address that will invite you to the second section. Let's see. Okay. Anastasia, what's your email address? Do you know?
So Toa Anastasia at go.byuh.edu.
Okay. See if you got invited as well. See if you got an email and it invited you. Does that make sense?
Yeah.
Okay. I'm going to close this one now and, well, why don't you guys, let's see. Can you see the email address or the invitation?
Yes,
all right.
I just opened it.
So can you get to, see, it should be on your Canvas now. See if you can get to the Canvas page.
I don't see it in my email though.
Yeah, I'm in.
You don't see it, Anastasia?
Yeah, I don't see it in my email.
Toa Anatasia, right?
Yeah.
Two A's? One user are ready to be added to the course. Do you see it now, Anastasia, or no? See if you can go to what's it called? Your Canvas page and see if you see section 2 on there.
My Canvas.
Do you see it?
No.
And you don't see any email?
No.
Is your email toaanatasia@hotmail.com?
I have that email too. I can check that.
Maybe you should, because it says that that's your default email.
Oh. I can check it because it's one might your class be waiting.
Yeah.
Yeah, I'll check it.
Okay.
Thank you so much.
All right, you bet. Bye-bye.
Thank you.
Bye-bye.
You are currently the only person in this conference.
I just barely opened it. The restroom. Okay, how are you guys? That's when you say stuff like, oh, I'm good. Hi, how are you? You know, that sort of thing. All right. Can you hear me? Great. Excellent. I'll say a little prayer for us. Dear Father in heaven, we're very grateful for the chance we have to meet together, to gather, and to discuss